Swayam Prabha. Digital India. Educated India.
Anyway, I think it's 9:30. We'll get started. I think everybody is here. So briefly, morning. We'll look through what we did the other day. Sort of some of these things, it helps me to, saving like this helps to quickly review what we did the other day. So when we pick back up, especially after a weekend. So what we looked at the other day was an elastic shock spectrum. We looked at a little bit of the influence of rise time. All of these topics, we are barely touching upon them. You can investigate further depending on your interest and what you want to do or whenever you apply it. Oh, this one I need to get you a good picture of it. Then we have seen what the influence response, what are all the differential equations, and we saw the deflection in terms. We will explore more about deflections in terms of the in terms of I. That was for rectangular loading, and for triangular loading also we have seen x. This is in terms of an integral, but there are expressions and response ratios in terms of either charts, or you also have equations. Then we looked at an example. This is an just to differentiate from what we will do today. This is an elastic shock spectrum. The shock spectrum, once again, is Td by Tn. That's the spectral range, and then the maximum response is the parameter. We looked at an example of Td by Tn and the influence of mass, especially mass and stiffness, the combination of those two. And this is these were two in the ranges of both impulsive as well as pressure ranges. And then we started looking at PI diagrams, and we've seen the application of work done, potential energy versus impulse momentum, and then kinetic energy that gets translated to kinetic energy and the potential energy, and saw the ratios. These are all for elastic responses and triangular loading. In this case, the impulses based on a triangular loading. And then we've looked at energy solutions for impulsive loading, and this is something I'll start off today. So we saw that if you consider impulse loading, then you can write delta max as a function of a constant L by D. This is an impulse, and E rho and D itself. And then the delta max is C2 P naught L by EB. So, and then in practice, the response regime is given out here. And then you have here the non-dimensional responses, and we've seen something on the PI diagrams. And what we were going to do was connect the PI diagrams to LOPs. I think, I don't know if I quite have that, but we'll be doing that at least on Tuesday or Wednesday. I'll show you the different LOPs. So that's where we stopped. So a quick example I'd like to start off with. All these had a lot of equations, but one of them I showed was the response in terms of here B is taken as 1 in many of these situations 1 unit, 1 feet or 1 meter. So you might see the B missing. So this is energy solutions for specific structural components. So we'll look at delta max, this expression, and this expression for quasi-static with a quick example. We'll start with that. So let's say this is an example using energy methods. And these are analytical expressions. I'm presenting a lot of analytical expressions because those are always what gives us some answers if we do advanced finite element analysis. So here you're given E is again, just be consistent in the units, and you don't need to convert whole back. One recommendation I have for conversion, what I do when I use SI is finish everything in the units I am most comfortable with and then convert final values, answers alone. So this way I'm able to judge the results. And so let's consider steel as a material here. So for the unit weight of steel is 500 pounds per cubic feet. Now for rho, we have to consider, this is the thing I'd like to point out, the mass density. In the SI system, kg is a weight, but in the other system, US systems or the FPS systems, mass is to be divided. We have pound mass and pound force. So usually pound is a weight. Here we don't talk of 200 in newtons as the weight, we talk of kgs as the weight, although it is technically not directly the weight. So you have here the mass density is 500 divided by, again, pounds per cubic foot. So divided by 12 inches and then 12 inches, and then of course the G. So mass density is W divided by G. So this is 1 by 386 let's say inches per second square. So you get this number to be equal to 7.5 into 10 power minus 4 pound second square. So this is pounds per cubic foot, pound second square per inches per 4. So that's a kind of an odd unit for a density, but you get that. So then our expression, I did not write. So the question is, given the following data, that L is equal to 5 feet and D, the depth of the member, we derived it for a cantilever. So the depth so this is your L and this is the D. You can adopt it for other situations as well. So D is equal to 12 inches and you're given a variety. We'll take 2 or 3 different cases, a variety of PR and IR. So those are the 2 data. Calculate the static, or we'll start with the impulsive. Then I've also looked at the quasi-static and also the static. The last one I've just presented very briefly. So the static is not quite right, but let me, at least these 2 cases we will look at. Deflections using energy methods. So we have E and rho, and so the expression that we had was so the main expression is delta max for impulsive regime or impulsive region or impulsive response, whichever you want to call that. So, delta max is given as C1 multiplied by L over D, then IR divided by square root of E rho multiplied by D, and C1 for the if you consider a loading something like this, for other, they all roughly come to around 2 plus minus range. So, let us consider an average value of C1 equal to 2.0. Keep in mind, C1 is dependent on the type of loading. So, let us proceed with calculating the parameters. So, square root of first E rho. So, let us start with E multiplied by rho. So, this is 30,000, and to be consistent, 30 into 10 power 6 psi, and rho is 7.5 into 10 power minus 4 pound second square by inches per 4. I never feel comfortable till I have the units associated all the time. So you'll see me doing that. So this number is 22,465. Huh? So 500 by 140. What did you get? Did I make a mistake? Yeah, this is pounds per feet cube. Now this is mass density. That's why I changed it. So I have to divide by G, right? So the weight has, so that's why I mentioned in your case, you would just take kg and divide it by meter cube. But when you're using the FPS system, when we say I'm 150 pounds, that's my weight. So we don't say you don't say if you're weighing 60 kgs, you don't say 600 newtons, right? Your weight is actually the mass converted. Am I right? So yeah, it's been a while since I've used the system. So, but that's the difference there. So anytime you use it in FPS system, make sure it's the mass. In your case, you shouldn't have a problem when you use kg and meter cubed. Mass is always in the mass, actual mass itself. So 22,465, this is pound second square by inches per 4. So now this comes to, when I take the square root, so this becomes 150, this is pound square, sorry. So pound square second square by inches per 6. So this one reduces to pound second by inches per cube. So therefore now we have delta max is C1, L by D is 5 feet. So and then so you have, let me see the expression. So this is delta max divided by L. So this should be delta max by L. So now this, or wait, let me make sure of the expression. I think I have a, wait, let me take this out. So square root, yeah, L square by d power 4. So yeah, L by d. So it calculates out to IR divided by E, square root of E rho is 150, and then divided by 1 over d. So you can calculate this based on your the IR value. So I don't quite specify. Basically, what I wanted to point out is make sure your mass, your units are quite consistent. So you get this in terms of now d is equal to 12 inches, and I don't know what the IR value I took. So anyway, this comes to 0.00033 IR inches. So if your IR, for example, is 1000 psi millisecond, the delta max comes to point. I'll check this a little bit more and let you know. I'll confirm that, but this comes to 0.33 inches. So the difference I wanted to show was, if you consider the same thing, the pressure, L, yeah, yeah, we will be using it here. Yeah, I've skipped a step, but you go through the calculation and then you'll get that value there. So the pressure is, the expression was C1 so X max is 3 L by D cubed PR. So this is just in terms of the pressure and E values. So this is X max divided by L. So in this case, X max, let's say the pressure is 50 psi, and so the X max in this case comes to equivalent pressure. Let's say this was IR and PR is 50 psi. If this is in the quasi-static range, you have to determine first of all if it is quasi-static, and then if you go through that, you can get 3 times 60 by 12 cubed PR multiplied by L divided by E, and you can get the E to be 30 million, and you can get X max, and you will find that X max values are much lower in this case. So for my case, I got in this case X max is 0.0075 inches. And an equivalent static load you can calculate. I haven't presented the whole problem as to how the loads are applied, but if you take an equivalent static load, those ranges depending on how the load is applied in the range of 0.0012. So you can get some nice ideas about what these are with the expressions presented in the energy methods. But so we also talked about the different regions of a PI diagram. So this is the normalized Pi. So this is the normalized pressure value in the y-axis, and this is the normalized impulse. And what we have seen is there is normalized, so this is 1.0 and 1.0, and it is asymptotic. So actually if you plot P versus R also, it sort of represents a PI diagram in some way. P versus R is also normalized. I mean, when you normalize that, you can get R if you represent it for impulse purposes. It also looks very similar to this expression. So we've seen there are 4 regions. A, we've looked at region B, region C, and now we've also seen that this represents an increasing damage. This is an iso damage curve. So this is where suppose you have a building or you have a structure that you want to assess. Keep in mind, this is used to assess the damage or damage level for a given type of building. So if let's say you're working with masonry walls or you're looking with concrete structures, concrete walls, you can develop PI diagrams. It takes a little bit of effort, but once you develop PI diagrams, they're sort of applicable to a little beyond what you have developed it for. So you can use it for other quick evaluation purposes and you have the levels of protections are given by several of these curves. These are all asymptotic. You can have, this is usually a very high level of protection. This would be a medium level of protection. This is a low level of protection, and this could be very low level of protection. So this is high deflection or damage. This is very low deflection or damage. So, and remember, A is no damage. These are all in this region of B. As you keep increasing pressure, if the impulse is low, increasing in pressure is not going to change its damage level. So increasing impulse is low means the time duration keeps coming down as the pressure goes up. And in the region C, if the pressure is fairly low, the normalized pressure, this is with respect to static. Recollect, this is P naught divided by 2 P naught by X static. X static by X dynamic, or K, I think there was a K involved. So region C tells you that you may increase your impulse as much as you want. If the pressure is fairly low, then there is no damage. The other way B is you can increase your pressure, but if the impulse keeps getting lower and lower, there is no damage. But then once you get beyond this region, then it gives you, for example, 2 degrees, say, and this is where I'll bring in some curves for levels of protection. This is, for example, 2 degrees theta is equal to 2 degrees. And this may be theta is equal to 8 or 10 degrees. In between, those are the values. So then when you have a structure, similar structure, all you do is you are saying, okay, my pressure value is so much, normalized pressure value is so much, and my normalized, remember x and y axis are independent, this is my normalized. So let's say this is point A, say at point A, this is the applied pressure and impulse for the structure. Then the level of protection is, you would go with the low level of protection. It is higher than M, lesser than L. So you go to the next level of protection. So if you want to increase the level of protection, either you have to push the barriers away or you have to strengthen the structure. Let me mention some notes of it. We are not developing a PI curve. So PI curves are generated with lots of simulations first. So for example, let's say you have a simple structure and let's say you are applying a PR and IR at this end. So then you normalize it, then you will find the delta here. So given PR and IR, calculate the response for each combination. And then you might have, let's say this is your PR normalized and this is your normalized IR, and you'll have a bunch of points all over the place. So if you're, that's why you have to really calculate hundreds of simulations, if not more, combinations. And especially finite elements, you can imagine you'll have, these are all, and then you take the points, let's say this is delta equal to 2, you'll find delta equal to 2, these combinations are delta equal to 2 or theta equal to 2, whatever. So all these points, isocores or points, these are points representing delta equal to 2 inches. So you get the idea how this is done. So to give you an example, let me just, you've got this one in, I'm going to switch the screen. So I wanted to show you an example of what we did a while, and there are numerous such examples. So we took reinforced concrete columns and we used finite elements analysis for this purpose. We used LS-DYNA and we also compared with a tool which we don't have anymore. I used SDOF also analysis. So PI curves were developed from FE methods are compared with curves from SDOF methodology. So we did sort of, when you do validations, there are a number of ways to do it. You can do numerical to experimental. That's one of the most commonly done in this field. Then you can do numerical to analytical expressions, and we are introduced a bunch of different analytical simplified equations. So that gives you a baseline or reference point, if you will. The other is to do numerical to numerical simulations. So SDOF methodology is a numerical methodology. finite elements is a little advanced, so you can do that. So that's what we conducted here. And what we did in this case is we talked about what they are, objectives of it. So we see these. So these are the different impulsive loading region, the dynamic loading region, and the quasi-static loading region. So this region, as we said, we talked about earlier, it's very difficult to do it analytically because you have to solve the differential equations. These expressions that we saw today, you can take the analytical expressions and then you can come up with those. Today's first example that we solved, you can use delta equations there, right? There you don't need to do any more analysis. Quickly run through a variety of PRs and IRs and then you can get deflections. So you will be able to get points in the impulsive and quasi-static loading regions. But to get this is a challenge. But so then we studied a bunch of seismic columns. So these are 4 types of seismic columns with different types of reinforcements and ties. So you can see that. And we've calculated a lot of, we ran, I don't remember, but it was hundreds of different scenarios. And then what I wanted to show was what are the different Z regions, the response regimes that were characterized for Z less than 3, the dynamic region, and then the pressure region, impulse region, dynamic region, and the pressure region. Then the deflection criteria, we talked about the S-beds and observations. So this is what, for example, it looks like. You see the curves, the different deflections. So 4.55 is the green and the blue. So this is the low level, this is the high level of protection. The top 2 are high levels of protection. Then the second 2 are medium levels of protection, increasing deflection 121.67. So this is 1, 2, then it is, so okay, here they are, 1 and 2 are here, right here. Then 3 and 4 are here. This is the medium level of protection. And you see that there is a difference. For example, this is, and then the high levels of protection are right here. So the orange is representing the S-beds and the solid lines here. So there is a big difference if you see between what LS Dyna predicted versus the S-beds. So also tells you that what did the finite element predictions do? Again, there are a lot of considerations. We will be talking about some of them this week. You will also have an experience about some of the easiness, the ease of using finite element programs, advantages and also the disadvantages, depends on material models and things like that. But then if you go through advanced analysis, you will see that your dynamic high LOP, right, using LS Dyna, this is the orange curve, is even lower than the S-beds. So here it's lower than this value. So there is a lot of, what does this tell you? If you were to make an observation between advanced finite element methods versus simple single degree of freedom system analysis, what does this tell you? There is a lot of, so the question is, if you are comparing single degree of freedom systems with advanced analysis, what observations would you, one observation would you make? It's O, which is, what is it? SDOF, right? Yeah, that's the main story here. You can save, if you're working in this area, it's worth conducting, spending the time, you have to evaluate that. So doing an advanced finite element analysis for the same structure, if that structure can be built in or something equivalent can be built in an LS-DYNA model, or something similar. You're looking at cantilever walls, for example, to protect your installation. And then those cantilever walls are made up of, let's say, precast concrete. Clearly, you can to an extent replicate that model in an LS-DYNA or simplify it a little bit. You can't represent each and every reinforcement that is out there, but you can clearly represent the overall concrete, and then you can also represent the main steel. You may not be representing the laps and things like that, but you can definitely represent the main steel. And then do the analysis, and then you can then draw curves like this. So, if you see for this case, I don't know if I have described it here. I can tell you the number of, tomorrow I'll tell you the number of analysis we ran. SDOF will probably be generated. Advantages in this case is if you have the expressions for it, the methodology, you can use VBA with Excel to generate these PI curves, because we've given all the expressions for pressure, impulses. You can calculate deflections, and then perhaps in about 30 minutes you can get the SDOF PI curve at most, 20 minutes, even less than that in a normal desktop. But if you do finite element analysis, you might take definitely a couple of weeks, a month, whatever, depending on the number of simulations you run. So, so that is the big difference. So, any questions on? Yeah. Yeah. You can't calculate a deflection. PI curve never used to calculate a deflection, but it tells you it stays within the damage, less than the damage region.
But it's the idea that this is the same deflection line, right?
Yes.
So that means the deflection is same in all the points, vertical line.
Yes.
So that means all these cases pressure was kept for the first get same.
Yeah.
Pressure was increased.
Yeah.
Deflection was formed same.
Yes. 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 That's definitely the case for the Y as well as the X axis. And here, if you see, I did not normalize it. I should have perhaps maybe worked on normalizing it, but here this is directly pressure and impulse diagram, pressure and impulse plotted directly. So anyway, that is, if you're interested, I can share this. The other thing is, so that is one characteristic of the PI curve. Second thing, keep in mind, not quite used to calculate. In some cases, as Amit was mentioning, you can, especially if it falls in the flat ranges, but in other ranges it is not used to calculate or estimate. We can estimate it, deflections given a PR and IR. And third is a PI curve is specific to a given structure, including the material and geometric properties. But given that, you can extrapolate a little bit for a similar structural type, because you cannot be generating for each and every situation like this. So the next one I've talked about, but maybe we'll just give it a number anyway. So, for example, let's say you're given an elastic behavior and K is equal to 20 kips per inch and W by G, which is mass, is 12.5 pound second square per inch. So, if you normalize them, normalize the axis, the x-axis is I divided by x max square root of km. Say x max, the damage level is 2 inches. And the area exposed, let's say it's a cantilever wall and the area exposed is 1000. This is just illustrative, nothing, not an exact example. So, in this case, I is, and it's a blast load. So, you have impulsive response or whatever response it is, P naught and TD. So, it's a triangular response. So, I is 1/2 P naught TD multiplied by the area, the force is there, divided by 2 inches square root of 20,000 psi multiplied by the mass is 12.5. So, this comes to x is 0.5 P naught TD. The y-axis is typically normalized to the static deflection, is P naught divided by 2 P naught divided by x max. So, this is 2 times. Now, the P naught versus x, remember, is often considered to be, so that is P naught versus x, not P naught versus TD. So, the P naught is, this is P naught multiplied by the area divided by 2 inches. So, this is 2 times P naught multiplied by 1000 divided by x max K, sorry. So, 2 inches multiplied by 20,000 pounds per inch. So, this gives y equal to 0.05 P naught. So, how do you estimate damage? Let's say you're given a PI curve. You have this cantilever wall, and I'll show you another example of a PI curve. So, you have a PI curve that looks like this. Now, if my pressure, say case 1, if P naught is equal to 10 psi, x is equal to this is 10, so 5 TD, and y is equal to 0.5. So, instantly you can see that for case 1, for any value you are going to rest only here. You are only going to get, immediately you can see that this will be no damage as TD increases. So, you can keep applying more and more the pressure for a longer time. So, you are really going to have no damage. Then only when for this you see let's say P is equal to 20 psi or 30 psi. Then X is going to be 20, this is 10 TD, and Y is equal to, let's say 30. So Y is equal to 1.5. So now you're going to have, and if the damage levels are like this, then you will start having points, say 1.5 is here, depending on the TD. So case 2 is depending on TD, the LOP of the structure, yeah, can change. These are just, I mean, some things you can easily, there's nothing new about what I'm saying, or you can easily deduce yourself, but then just shining light on how to interpret these. The first time you see, at least as I mentioned earlier, took a little while to get a grip on what these are and how to use some of them. So as an example, okay, so if you see here, this is specific incident impulse. I have to find a way to import it with a reduced size. I think that may be the issue. So here you see that this is for different damage levels, damage level A, B, C and D, and you can also draw this for different, you can overlay, this is going a little advanced, I am not going to get into it. Some of the equations I showed you, or maybe I did not show you, we were trying. You can plot the range on the same curve. If you plot pressure and impulse, takes different ranges. I mean, you can represent multiple things in the same curve, but what I wanted to show you was this was developed for a brick wall. Yeah, even though it was developed for a specific size of a brick wall, you can use it in general for other brick walls as well, if the different thicknesses, at least to get some ideas. But this is how a pressure impulse diagram looks like. And note that you can represent different advanced representations or other representations. You can include different types of explosives here for here they are basically plotting range versus pressure. If I had given a range equation, or maybe if I hadn't given, I can give you that equation. If you have a range equation, you can you can calculate, given a W, you can calculate the range over WZ over pressure and then the range, and then you can plot it in this itself, and other interpretations are also possible. So I think that's all I'll spend on a PI diagram. I wish I had that other program where you could generate a PI diagram. It was really nice, but it's not available anymore. But maybe one of you could take up projects, or if you're interested, we can talk about some ideas. If you're working in the building side of things, how to develop. I know the US Defense had developed a lot of these diagrams for different types of structures. So that is something as a developmental project also can be considered. So for example, the SDOF and whole Excel program of an SDOF response. So you give a structure, maybe you can develop it for steel, concrete, masonry, precast, pre-stressed, anything that you want. So your inputs are going to be the structure properties, what are the sizes, usually if it's a wall, 1 meter width or 1 unit width is considered, and then developed all the section properties as we will discuss in the next couple of classes, and then develop the response of it. But you have to build all of this with a VB interface, and then all the LOPs you can get the actual deflections, ductility ratios, and then what is the LOP afforded, and then for that case you can even plot or PI diagrams all in one program. So any questions? We're going to now move to a slightly different, the next topic. So the next is, so far we have considered elastic response. Now we will look at the elastoplastic response. And primarily the reason is, in normal loading and under your elastic response is sufficient. However, when you consider blast loading, the full capacity of the structure material is called upon to act. You are utilizing the entire capacity, in this case, whatever be the in situ material properties, and also any redistributions and other such things from a structural level is considered. So, let's say you are loading a structure, load versus your deflection. Now, if you look at different types of buildings or different types of materials, say you're plotting P versus delta, you can have a response that looks like this, and it may even go. So, this would be for a steel structure. So, you're analyzing a steel beam, steel column, other such things. You could have a response something like this. It's quite ductile. Even in concrete, it does have some, but clearly it does go down. It's more brittle in nature. That's why people are working on things like, I think we're going to have a presentation, when is by Mutturaju? Tomorrow, right? So, Mutturaju is working on UHPCs. So, if you go UHPCs, perhaps you might see, and I'm just guessing, you might see a better response. So, this may be with UHPC. So, you'll see a very nice presentation on this tomorrow. So, you can get a lot more ductility from a material perspective by using, so improve ductility by detailing or fiber reinforced concrete. UHPC part of it is also using fibers, different types of fibers. Then you can have, of course, brittle behavior, pure brittle behavior with practically no load capacity maintained at the peak value. That's why in seismic, the columns that we studied, it had a lot of seismic detailing, and in that paper you will see the response is also based on the type of detailing. That's what I meant, improved ductility by detailing purposes. That's diamond stirrups that you saw, or rectangular stirrups, or the spacing of the stirrups, all those play in improving the detailing of the structure. So, for example, concrete detailing considerations often are based on seismic detailing ideas, because seismic detailing has been really well developed. So, borrow from the work done. So for example, columns with with different variety of stirrup types and distances, spacing I should say, not distances. Same thing with beams with enhanced shear detailing. Quite often flexure detailing is not as critical once you start getting into the blast type loading in concrete structures. To get the response that you need, for example, even at high level of protections, if you want to get a response of 8 degrees, you really need to focus on good detailing at the shear ends, wherever shear is high, ensuring integrity out there and then making it more ductile in the process. So, we borrow these concepts and we've discussed the idea of a resistance function. So, let's start implementing that. A resistance function is nothing but a force deflection response curve. It is not a predicted curve. I mean, we do predict it for design purposes, but typically it is again how a structure is going to respond, either from experiments or this is from numerical methods, numerical, analytical approximations. You can never predict an exact force response curve using analytical expressions, but that's often the only way in design. So, for example, if you look at RC, this is R versus delta. If your numerical curve looks, your experimental curves looks something like this, then for SDOF purposes, using non-lin, you can break it down into, non-lin allows 3 different stiffnesses to be incorporated. Non-lin gives you this resistance point is P naught. So, we will be using non-lin for all our examples. In non-lin, P naught is the strength. We'll call the strength, we'll see how to calculate the strength with a variety of examples. And K1 and K2, so this is your initial stiffness K, K1, K2. So K, K1, K2 are, or just K and K1 alone, stiffnesses to be input. And these stiffnesses are either in newtons per millimeter or newtons per meter or in pounds per inch. So the system itself solves three different equations depending on how many that you provide. So the equation for solution in nonlinear is written as mx double dot instead of kx. This is the, or if you are developing your own. So far we have talked of mx double dot plus kx, right? K is the stiffness multiplied by x. But in elastoplastic systems, so the differential equation, if you are solving one, if you are, let's say, you have a specific system, and I'm addressing this topic, this course, both from a research and design perspective. So, from a research perspective or research or development perspective, you can use this concept for any type of structure. So, the differential equation has a small difference. In this case, we replace kx by r, which is the resistance function. So, you have here r as a function of x is equal to, on the right hand side, p as a function of time. And the resistance curve can be a numerical expression. So, we won't get into solving it, nonlinear is doing that for us. So, if the resistance function has three different expressions, is kx for x less than or equal to x1 or k delta, or let's say k, yeah, let's keep it as x, and is equal to k1 x for x1 less than x2 equal to k3 x for x greater than. This is in nonlinear. And you might ask me what stiffness values you should input if you do not know, because you can calculate the initial stiffness, but calculating the subsequent stiffnesses is going to be a challenge. If it is steel, steel is rigid plastic. So, steel structures, this is P naught versus delta. Here you have, this is P naught and this is K, and here you see that it is K2 is 0. You can input anything like whatever you want, a low value, 10% or 5% of K. You can try out to see, try different small values to check for sensitivity. Sensitivity of the response, and from that make decisions. Decide which one to use. For concrete, you can try Concrete, if you see, you have several expressions. Stress versus strain. You have the one of a very commonly used one is the Hognestad's stress strain equation. Are you familiar with that? Heard of that? Some of you have not heard of it. Not heard of Hognestad. It's basically equational representation. I wish I had. Do you remember what it is, Kavi Rasu? Do you know the expression for that? You can Google it, and the stress strain equation. I don't know if you can Google on now and let me know. Is there a way to it's a equation in terms of your peak strain, and it's a cubic function or something like that. We can from that itself you can get an estimate of what K2, where the typically your elastic response now, given that, you'll see there is a little bit of anomaly when we do design. The elastic response is F less than 1/2. The term F, it's FCK here, right? FCK. We use the term FC prime. This is, and you might see me use FC prime by 2. That's the same thing. So, and then you up to that stress, and then you can calculate your stiffness, basically the slope from that expression. You have anybody have an expression or? Sigma C is equal to FC. FC is the FCK, right? Yeah.
2 times epsilon c by epsilon c naught
Cube, no?
minus epsilon c by epsilon c naught square.
Epsilon C by. This is C, both are the same, right? This is C naught. Like this?
Yes.
So, and epsilon, so this is epsilon C, and epsilon C naught is the peak value here. Is this epsilon C naught? I think so. Or maybe, I don't know if it is it's a peak value, yeah. So, typically epsilon C naught is considered for normal concrete. It may be a little different here, but peak is around 0.003 in some countries, 0.0035. Europe and India probably is 0.0035. It's 0.003 there. And it's a non-dimensional equation. So FC, you can, and this equation is valid for both systems. So then so we will look at a hand, when you do hand calculations, we use elastoplastic shock spectrum. So the graph itself, the response ratio, let me plot the elastoplastic shock spectrum. So you have here on the x-axis and the y-axis, and there is also 2 other axes that are representing the same thing. So x-axis is delta, just like you had in the elastoplastic, delta dynamic by delta static. The y-axis, x-axis is Td by Tn. And these two axes, both this one and this one, represents Rm by F naught. I think that's the, yeah, Rm by F naught. And Rm, this is the resistance, maximum resistance divided by the applied load. And it's a non-dimensional ratio, a non-dimensional quantity. And here you'll see curves that go like this. For different Rm by F naught ratios. So, if you see, it starts with 0.1 to 0.8. So, 0.1 to 0.8. So, that tells you that the resistance in here is more than applied load. Sorry, resistance is less than applied load. And here it goes from 0.9 to 2.0. In this region, the resistance is greater than applied load. And it makes sense, the deflections are dropping. Here the deflections are increasing. Let's look at the numbers. It's a log scale going from 0 to, seems pretty unreasonable. This is 1, 10 and 100. So, the ratios jump. In the previous case, what was the maximum ratio? 1.7, right, for a triangular load. So, here the ratios jump from 0 to 100, and you might wonder, there are some other curves I'll show you. So, we can use this. So, the steps in this case would be to calculate the resistance. We'll look at how to calculate the resistance Rm in kips or newtons for the given structure. And then I know you're coming from a variety of backgrounds, so I'll go through all the details so that you're not lost in the steps. So, even though you calculate a moment resistance or a shear resistance, you convert it to an if moment resistance is converted to an equivalent force resistance, and then calculate the applied load P naught, again from the pressure values. This is again in kips. So, the pressure and areas is what you can use, and then calculate Td, Tn, and given Td, you find Td by Tn. And then once you do that, then you have, for example, you're given a Td by Tn, say Rm by F naught is something like this. You're going here and then you find out, calculate or determine the delta dynamic by delta static. And delta static is typically P naught divided by the elastic. For again, these are all for design purposes. So this is the hand calc method. Or analytical expressions. You can also use, as I said, to find delta dynamic, and we'll go through exercises to compare both. You'll see what differences they are. You might ask, why are we doing both again? Remember how conservative SDOF is, right? SDOF can be quite conservative in estimating, as you have seen in the paper that I showed you. So you need to have, till you get an idea of how conservative it is and how to use it, it's always good to compare with two different, in such uncertain, in blast analysis or design, I would always, I don't think you'll find this in any book or anything like that. Always, my personal recommendation is to do either a numerical to numerical comparison, such as the chart to nonlinear, or this is one example, or do a numerical to analytical, which is the equations comparison. So the numerical, for example, SDOF versus equations, or charts versus equations. One of the, again experience, you'll find your delta, given your RM, applied load, your resistance, you might say delta dynamic to delta static is 55. That makes sense. I don't know. Right? How do you know? Come find some other way to get some numbers and see if that really makes any sense. Any questions again so far? So I won't insert it here as we are having issues, but what we'll all upload is these curves. I think I have 8 of them, but you'll use most of it in the you can use this also. So this is maximum deflection of elastoplastic single degree of freedom system for triangle load after the UFC 3-340O2. So you should find it in the UFCs also. So XM by XE, I think during the break I'll see which curve it is, or lunchtime I'll look at it and let you know. If one of you find out, let me know. So this is XM by XE. What you see here, this is a triangular load. You see the resistance function. The resistance function is Ru and Xe. So the stiffness that we calculated, using the stiffness you can find X sub E, and the displacement function looks something like this. So Td by Tn, Xm by Xe, the same thing what I showed you just now, 0.1 through 2.0, right? This is a little bit more, same thing that I inserted. But what this also has is maximum response time for a triangular load. We haven't looked at the response time so much. This is Tm by Td, the time to where you get the maximum response. So this is given for a triangular load. Then this is the maximum deflection for a gradually applied load. So this is P naught versus T. This is a little more quasi-static, and the resistance function is still the same. So if you compare the responses, you see this is so different. That is one response, and here you see this is very similar to your static type response, especially as your RU resistance by P keeps increasing. The XM by XC is almost equal to 1 or something like that. Then you have this for the maximum response time. Then this is the maximum response for a rectangular load. When you say rectangular, it is P naught versus T. Remember the shock wave versus the blast wave type situations. So there again it is different in the high load, high resistance regions. And then finally, this is for a triangular pulse load. So if you have, this could be useful for petrochemical facilities where you or the sidewall responses you are calculating, you have more of a pulse load and approximations are made. So in your case, you should take, and then the same thing, maximum response time. So we will call this XM by XE and we will upload it in your folders. So we've seen all of this. Another thing I wanted to mention is we will upload this as well. I promised you on Friday. It's the same UFC curves, but these are numbers for SI systems. So if we do any problems or you encounter any problems in the future, one is for hemispherical charges, and that is air burst, and this is the spherical is air burst and hemispherical is the surface burst, similar to what you saw in UFC, but this is in MPA systems.